All right, welcome back, students. This is the second part of video lesson number 1. The first video was getting kind of long, so I broke it up into a second video to start with the next couple examples before we do your first homework assignment. All right, so we introduced what a vector is, and we talked about how to find a vector given 2 points, and we talked about the magnitude, how to find the magnitude of a vector. Next thing we want to do is some vector operations, okay? So there are 2 operations we want to do: adding 2 vectors and multiplying a vector by a scalar. Okay, so suppose you have 2 vectors. Vector u will denote as u1, u2. Vector v will denote as v1, v2. And k is a real number called a scalar, okay? And that word in math, a scalar is some constant that you multiply by something. Usually not a number though. Usually multiply a constant by a vector or a matrix or something like that. And something that makes it larger or smaller to scale. If you ever heard of drawing something to scale, a model may be drawn to scale. That's where that word comes from, scalar. You make something larger or smaller proportionally. Anyways, back to this. The nice thing about both of these, vector addition and scalar multiplication, is they both work exactly like you would want them to work. There's no tricks here. Now, vector multiplication later, that gets a little trickier. There's actually 2 ways to do it. But vector addition and scalar multiplication is really simple. So let's start with the first example here. Vector addition. All right. Suppose that I want to add these 2 vectors, u and v. Well, you might think, how would I do that? Well, maybe I should add the horizontal components together and add the vertical components together. That might seem logical. But guess what? That's exactly what you do. So we're going to add the horizontal components. So u sub 1 plus v sub 1. And then we're going to add the vertical components. U sub 2 plus v sub 2. Okay. Which again, if you think about that, it should make sense. You're just adding the 2 horizontal components to the new horizontal component and adding the 2 vertical components to get a new vertical component. All right. Now I want to draw what that looks like on the xy axis here. So what does it look like to add vector u and v? Well, let's draw 2 vectors. It doesn't matter what they look like. Well, let's say that's vector u, and let's say that's vector v. Okay. Now, you might say, how do you add u and v together? Well, what is the resultant vector going to look like? Well, what we do is we call the head to tail method. You put the head of one vector on the tail of another. Remember, I can take this vector v and move it around horizontally and vertically as long as it has the same components, it's the same vector. So let me draw the vector v. I'm going to try to draw the same length, the same direction. Draw right there. Okay, now, what is the resultant vector? Well, if you go from the beginning of vector u to the end of vector v, in other words, if you complete that triangle, from the beginning of u to the end of v, that is the sum u plus v, okay? Now, notice, vector addition is commutative. Remember the commutative property? Addition is commutative. 2 plus 4 is the same as 4 plus 2. Well, same with vector addition. What if I took the vector u and put it on the end of vector v, right? I would end up at the same spot, okay? So vector addition is commutative. In other words, u plus v is the same as v plus u. All right, which again should make sense because the addition there and there is commutative. All right, so that's visually what u plus v looks like. Take vector v, stick it at the end of vector u, and then go from the beginning of u to the end of v. All right, we're gonna do this later and get to application problems to visualize adding vectors. That's what we're gonna do. That's how you do that. All right, next, scalar multiplication. All right, so draw a vector u. Now I'm gonna ask you a question. What do you think vector 2 times, or vector 2u looks like? If I were to say 2 times vector u, what would that look like? Right? Um, actually, let me give you a moment. Draw what you think right now. Take your pencil. Draw what you think 2 times vector u would look like. Well, hopefully you drew a vector in the same direction as u, just twice as long. So, like that, right? So the vector 2u is the same direction as vector u, just twice as long. 3u would be the same direction as u, just 3 times as long, etc. Okay. What do you think negative u would look like? Let me ask you that. What do you think negative u? Well, if you took u but went the other direction, okay, so in other words, you flipped around the head and tail, that would be negative u. You just basically flipped around the head and the tail. Or you could also stick it on the end. Go, follow the same line there, but just going the opposite direction, the same length. That is also negative u. Either way you could represent it. So how do I do scalar multiplication? How do I take vector u and multiply it by k? Well, once again, it works exactly like you would expect. You simply just multiply each component by k. So k times u sub 1 and k times u sub 2. Okay. Basically, you're almost like you're distributing the k to each component. It's not distributed property, but similar idea. Okay, so that's how we do scalar multiplication. So hopefully, as you can see, the math there isn't too difficult. It works exactly like you'd expect. All right. So let's do now a couple examples of that. I'm going to give you two vectors. Vector u is negative 1, 3. Vector v is 4, 7. Find the component form of the following vectors and draw them on the graph. Okay, so first one, draw u plus v. Well, then why don't you draw u and v separately? So negative 1, 3. So start at 0, 0, go to the left 1 and up 3. Okay, that's vector u. And then 4, 7. Go to the right 4, up 7. That's vector v. Okay, now what is u plus v going to look like? Take the vector v, put it at the end of vector 1, vector u, or take vector u, put it at the end of vector v, and then draw the vector you end up with. That's u plus v. Okay. Mathematically, what are we doing? Simply add the x components, add the y components. So negative 1 plus 4 is 3. 3 plus 7 is 10. So you should end up with the vector 3 comma 10. All right. And so let's see. I'm going to take the vector u, put the end of vector v. So from here, I'm going to go to left 1 and up 3. Right? There's vector u at the end of vector v. And now, what does the resultant vector look like? You start at 0, 0, and you end at 3, 10. There you go. There's the vector 3, 10. So hopefully, visually, that makes sense, what we're doing there. All right, next one. What is 3 times vector u? 3 times vector u. Well, once again, I'm going to draw vector u. Okay. 3 times vector u is just going to take each component, multiply it by 3. So 3 times negative 1 is negative 3. 3 times 3 is 9. So negative 3, 9. Okay. Now let's draw that. What's it going to look like? Negative 3. We can count there, 9. There we go. That's 3 times vector u. As you can see, it's going in the same direction as the original vector. It's just 3 times as long. So that's vector addition. That's scalar multiplication. Okay, one more. This is kind of combining these two together. Scalar multiplication and then vector addition or subtraction, which again is just addition with a negative. So do 4 times vector u, and then do 2 times vector v, and then subtract them. So once again, why don't you pause the video, try that yourself, and then start it again and check your answer with me. Okay, so first let's do 4 times u. Again, the same u and the v we started with up there. So that's going to be negative 4 times 12 minus, and then do 2 times v, which should be 8, 14. All right, and then do negative 4 minus 8 is negative 12. 12 minus 14 is negative 2. So there you go. The component form of 4 times u minus 2 times v is the vector negative 12 comma negative 2. So again, like I said, the math there hopefully isn't difficult as long as you understand just the terminology of what it's asking you to do. And the notation, how to write the vectors. All right, last thing real quick to wrap up this first video lesson. A unit vector. What is a unit vector? Do you remember the unit circle? Obviously you do, but what does that mean? Why was it called the unit circle? The unit circle was called that because it was a circle with a radius of 1 unit. Okay. So just likewise, a unit vector is any vector with a length of 1 unit. A unit vector is a vector in the length of 1 unit. And usually we talk about unit vectors, we talk about the unit vectors in the horizontal vertical direction. So like 1, 0, 0, 1. So the 1, 0 is called the vector I, and 0, 1 is called the vector j. Those are what's called the standard unit vectors. One in the horizontal direction, one is the vertical direction. If you get to three-dimensional vectors, they use IJK for the 3 dimensions. So any vector in component form can be written as standard unit vectors. All right. All this is, boys and girls, is different notation. So don't confuse that. I just want to show you the notation because your textbook uses both, and different books you see will use different notation. I just want you to be familiar with that. So if you see component form A comma B, all that means is that A is how far you're going in the horizontal direction, as we know, and B is in the vertical direction. So you can do A times vector I plus B times vector j. Okay. And again, when I write the unit vectors, the way I was taught to write them is to write them with, instead of the dot on the I, we put the little arrow for the vector. So if you see something like this, A times vector I plus B times vector j, all that means is it's the same as A comma B. All right, it's a component form. So again, just different notation to write the same vector. All right. So if you hear, that's what's called the linear combination of I and j. It's kind of how you might hear the book phrase it. So if you see the book say something about linear combination of I and j, again, that's just a different way to write a vector. Right. So let me just do an example here real quick. Let me write a vector in component form. Let's say, or was it right, the vector -3, 2. All right. In IJ notation, the horizontal component is -3, so -3 times vector I, and the vertical component is 2, so 2 times vector j. All right. So like I said, these mean the same exact thing. They're just two different ways to write the same vector. So please don't let the notation confuse you. All right. You might see different ways. So your homework now. The first homework that I want to give you from the textbook is on page 456. Please do problem numbers 2 through 7 and 13 through 20. Okay. So now, real quick, when we look at those, all that should be stuff that we did in these first 2 videos. Okay. 2, 3, and 4. It gives you 2 points R, or 4 points, R and S, P and Q, and find the component form of R, S, P, Q, and show that they're the same vector. You should get the same answer both times. Okay. And then the next section here, 5 through 7, it gives you 4 different points. Just find the component form of the vector and then find the magnitude of that vector. And then the bottom section, 13 to 20, it gives you 3 different vectors, U, V, and W, and it just wants you to practice the vector operations, either adding the vectors or multiplying by a scalar. Okay, so go ahead and try that first homework assignment, and then share your work with me when you're done so I can check it. And then in a couple days, I'll post another video with some more lessons over vectors.